Welcome at our today's webinar. Here we have Eugeniusz who will present and tell us something about nuclear energy and space exploration. So I think that we can start now.
I want to introduce you the future of nuclear energy for future of space exploration. Basically, I wanna introduce you its three parts. At the beginning would be the aircraft, so jet engines, then classical chemical rocket engines, and after that, the final part would be the most important one and the most interesting, in my opinion, is nuclear propulsion systems. So let's begin with the basics. How do those how do these aircraft generate lift? Lift is a force causing airplanes move up. And to explain this, we must dive into some physics here. So I inserted here the right side two images to help me help myself to explain this. As any thoughtful aviator knows, wings are the true architects of flight, but how exactly do they conjure enough lift to raise in an aircraft to the skies? Let's begin with the first image here, representing forces that act on the wing itself. We have an blue arrow indicating this is a relative wind blowing in the direction opposite to the direction of motion of airplane. Airplane is here, so the airplane goes at the left, and the relative wind, so molecules at the right. They have opposite direction, and the wing itself, or we could say chord line here, represented in red color, isn't parallel to this relative wind. There's always some angle. This angle is called angle of attack. And we could say that air molecules which fly here at the bottom side, sorry, at the bottom side, on the wing bounces off this side of the wing and change trajectory. We would explain this in the terms of second law of Newton here in the right bottom corner, as if there is a momentum change, then some force must be applied to generate this momentum change. And here you can imagine that those molecules just bounce off this bottom side. So if they bounce off, they change the momentum, and if there's a change in momentum, so force from the wing side must be applied down. And from the third law of Newton, we also know that if there's some action, there's need to be some reaction, and reaction will be this force causing this force going up. And this force causing the aircraft to go up is called a lift, is represented here with this green arrow. But it's not the only component which is responsible for this, because when aircraft moves very fast in this area, we can imagine that this area compresses here and creates a high pressure zone. So those molecules, when they move to the right, they split into two parts, in the bottom one here and the upper one. In the bottom part, of course, majority of molecules go here at the bottom, and the other part go up. So when those molecules go up, they are in fact accelerated. Why is that? This is the reason for that is here is created a zone for lower pressure in this area, and here, as I said, the zone of high pressure. So we have a pressure differences, and because of that, our molecules accelerate and go up with a greater speed than those molecules going forward at the bottom side of the wing. So here is the zone of lower pressure, and here is the zone for higher pressure. Yes, high pressure, and this pressure difference generate additional lift to our system, and those pure lifts counting from molecules bouncing off this side of the wing, and because of the pressure difference at the bottom and the up, we can sum it up, and we would obtain this pure lift. I would say pure. I would explain why in the moment. And the additional force we have to include here in our explanation is the drag, because it's always here presented in the system. This is the same thing as the second image indicated with D, drag. This drag is created because of if there is an angle of attack, there is always some turbulences at this. There's always some turbulences at this area, and this turbulences causes that our aircraft pushes backwards in some way, and this is this force called drag, and the sum of this lift and drag, as this picture stated, is a resultant force, and this resultant force is, I would call, a real lift that we observe in aircraft, because this is the force that engineers count in their calculations to actually project something. And you can see, you can hear in addition that in this image, the weight of the aircraft W going down, and the lift this letter L are not parallel. I mean, they don't have those 180 degrees between them, but there's always some angle theta. This, and this is because of this drag. We have to account to the lift to tell something about the real lift in the system. So we can also add a thing to our system with aircraft. I mean fuel storage. Fuel storage also influences an aircraft stability here. Locating fuel tanks within the wings, so in this area colored in yellow, causes it to not flex during the flight, because if we would imagine this weight at the center part right here is very large force, because there is a center of mass of the aircraft, right? And here at the wings, lift is generated. So if we would not balance this lift at the wings, our aircraft would look like this. So some flakes effect is it called. So to balance out this lift on the wings, we have to have here some fuel stored, and this fuel generates some weight to counterbalance our lift. So our plane, while flying, this is not like this, but this. And I would introduce you a quick theory about one theory that I found, and this is incorrect one. A widespread but flawed explanation of lift claims that air splitting of the wings' leading edge must reunite simultaneously at the trailing edge. This is basically as you have here lower streamline of the red color, and the butter streamline with the blue color. This theory just states that those streamlines have to meet at the same time here. This is not true, but this theory was been taught for many decades. And actually, when I've prepared the material for this webinar, I've encountered this I like a lot. So this is just not true, because this theory can be appealing because it states that at the bottom side velocity is lower, and so pressure is higher, and the upper part pressure is lower and velocity is higher. This is true. We know that from here, as I've explained, but the reason for this is wrong, because this theory just states that they have to meet, but there's no such a law of physics that tells us this is true, just some assumption that had been proven in the experiments later that is not true. As we've discussed, the lift force acting on the wings of aircraft and causing it to move up. The next part is the thrust. The thrust is the force generated during a work of aircraft to move it forward. So if we add this thrust force, which causes the aircraft moves forward, and the lift, which causes aircraft moves up, you adding these vectors get some vector that explains in which direction this aircraft actually flies. And I've inserted here two images of two most popular jet engines, here turbojet and turbofans. Turbojet is one of the simplest, so I would explain the most terms in turbojet, and turbofan will be explained later. It's the addition because it's basically turbojet inside a bigger engine. Okay, here you have the image at the left, some blue arrows which indicate that there is mass flow rate, some intake into the engine, and ambient air enters the front of the engine and passes through a series of compressor blades. Those ones here, and the next ones, they are more and more thinner. Those are blades which accelerate, which accelerates our air molecules and then convert this kinetic speed the air molecules have got from the blades, then converts it to the pressure. So this is basically what compressor does. It increases the pressure, and those air molecules go in forward. Here you can see this cavity is at the end is very. It's not as big as it was here. This is the additional effect you need to account because to talk about some compression, so increase in pressure. And this mass flow of molecules enters the next stage, so-called combustion chamber, where the combustion reaction occurs, where basically hydrocarbons, nowadays it's mostly hydrocarbons, but there are some tendencies to seek for alternatives, more ecologic and so on. Here, the air molecules react with hydrocarbons to produce CO2 and H2O. Those products with unreacted nitrogen, because nitrogen mostly is not reactive in these conditions. This gas has a separate name, and it's called exhaust gas. So it's CO2, H2O, maybe some unburned fuel, and nitrogen which hasn't reacted. And after the combustion chamber, where of course the temperature is very high, pressure is also very high, this exhaust gas goes to the next section. Next section is here. Here is it's called the turbine, which also have some blades, almost the same one as it was in compressor section, but they are thicker because here those blades need to withstand very extreme conditions actually compared to those blades. Here the gas is very hot, pressure is very high compared to this section. So the hot gases next drive to a turbine, which is a series of blades mounted on the same shaft as the compressor. Shaft is this element which connects turbine blades and compression blades. So if those turbine blades drives because of the influence of this exhaust gas, though this basically this gas does some work on this turbine blades, and this work, so energy is transferred through this shaft, causing compressor blades also to rotate. And if they are rotating, they accelerate in the air molecules and causing it to move forward, and the cycle is completed. And the final part, after the turbine, this exhaust gas goes to the so-called nozzle. This gas is accelerated through a nozzle, and is being thrown out to the outside. And so this is the full cycle in very briefly, because we don't have so much time to dive deeply into this. And so turbofans at the right side, this is basically simplifying the same as turbojet, but with addition huge fan in here, located here, behind, in front of a compressor of the main engine. This turbofan works very similarly, but also a bit different. The difference between turbojets and turbofans is that most thrust generated in turbofans come from the air which bypasses, so it goes here and here, bypasses the our turbojet section. Let's call it that way. And in general, this is called bypass ratio, the ratio of this bypass air coming through here and here to the mass, the airflow of which passes through the turbojet section. This is a very important quantity, because the bigger it is, the better. Because you don't need to burn as much, a lot of fuel to generate as the same thrust, basically. The part of it just comes from this bypassing air, so for free, let's call it. And the average bypass ratio in modern aircraft is 5:1, 6:1. In the most extreme cases, it can be even 10:1 or 12. As one example of this is this engine, gigantic engine, General Electric's GE9X, is the world's largest commercial aircraft engine. The fan is enormous, 3.4 meters in diameter. This beast, and has a bypass ratio 10:1. So most of the thrust is generated by flow of bypass air. And of course, it's optimized for subsonic space, because modern aircraft, commercial aircraft, are using this turbofans because they are very efficient. You don't need to store as much fuel, and you generate a lot of thrust here. So coming back, this is how this engine looks like in cross-sectional area. At the beginning, you have those blades of the compressor, and here you have combustion chamber, and the last part, the blades of the turbine. And you can explain it in terms of thermodynamics. How does it work? And this is called, in the case of aircraft, the Brayton cycle. The Brayton cycle is represented more frequently as the diagram. On the y-axis you got temperature, and the x-axis you got entropy. So at the beginning, this section indicated with 0, some air is sucked in to the engine, and you just increases the temperature. Pressure is paradoxically the same. As we can see, the pressure is the same, and after being sucked in, the air, of course, goes through the compressor, and this compressor section is presented here with this blue arrow going up. In this compression area, of course, pressure is increased and the temperature is also increased, but the entropy, this is the most important part, entropy is constant. And after the compressor stage, the next stage, of course, as we remember, is the combustion chamber, represented in this arrow going up. And in this arrow, of course, temperature is increasing very fast. And so the entropy, because here the reaction occurs, and if the reaction occurs with more chaos to this is how we can understand the entropy as a physical thermodynamical quantity. And this entropy increases as and the temperature as well. And after those air molecules goes completely through the combustion chamber, they are in the turbine section, and in this turbine section, this gas does some work on the turbine blades, and of course it loses some energy. This is indicated in temperature going down. Yep. And the final stage is the nozzle, and with the nozzle the temperature is also decreased, but entropy, of course, there's no reaction occurs, so the entropy is constant. Of course, you need to remember that this is an ideal situation. Ideal situation means that, for example, those squares, this and this, must be equal, because this is the section of compressor and this is the section of the turbine. If there are no losses in transferring of energy, transferring of energy from the turbine through this shaft to the compressor blades, so if there are no losses, so the temperature difference must be the same. But of course, it's not true. In reality, it's an idealized version of it. And the most important part, of course, during this combustion chamber, we don't want to pressure to increase and or basically change in any direction, and we don't want to for energy losses here to occur. And I've told you about this best example of the jet of turbofan, sorry. And at the right, you have an example of turbojet. Is a G58. It's an engine developed for achieving Mach 3 plus speed, used in reconnaissance aircraft like, for example, SR-71. The characteristic trait in this engine and some series of engines used in military, they may have an afterburner. Afterburner would come if we see here, sorry. Here, after the turbine, you have exhaust, but afterburner comes after the turbine, so before the nozzle exit. And this nozzle exit, there is also a reaction occurs, increasing temperature even higher, and if you increase temperature, you gain more thrust. So this is the reason why turbojets can be may still used in military aircraft. Okay, that was the part for aircraft engines, turbojets and turbofans. And now we would analyze the most important ones, the rocket engines. They differ fundamentally. They carry both fuel and oxidizer on board, aboard, because the aircraft must have only space for fuel, and the oxidizer, so air in oxygen in the air, O2, is for free because we have an atmosphere. Yeah, but rockets fly beyond the atmosphere, and there's no air and no oxygen, so you have to need a separate tank for the oxidizer and a fuel. A separate tank for liquid rockets, but we'll discuss it later. And this added mass, because of a separate fuel or additional mass of oxidizer, demands, of course, greater thrust for lift off and acceleration, because of the main goal of any rocket is to achieve escape velocity. I mean, 11 kilometers per second or something like that. And if you want to achieve such high speeds, you need an enormous thrust force, causing that you move up. Okay, the most important part, and we will focus only on that part, not, for example, materials and so on. We are interested in combustion chamber and propellants, because in the nuclear propulsion systems, which we will discuss in a moment, this is the most important part, because the heat source and how is it converted. It's basically the same topic. So within a rocket's combustion chamber, propellants, it can be solid or liquid. On this image here, you have liquid oxygen and liquid hydrogen injector. So they are. So this is an example of liquid rocket, but it's for now it doesn't matter for us, because during the combustion reaction, they eventually go to gaseous state. So for now, it doesn't matter for us. And this gas created in the combustion chamber presses against the chamber walls and is forced through a nozzle that first converges. So it's on this image is here. This is the section of the nozzle where where it converges. Here you have a throat or neck. Here is called neck, and the next part is a diverging section of the nozzle exit. The next very characteristic thing for a rocket, which is different from the same ones in aircraft, lift, and lift is created, of course, by a combustion reaction here, because it's the exhaust gas, exhaust pressure on this side here, the up direction. So this is the direction where the rockets fly, the up. But lift and speed are generated in the same place. The combustion of fuel of course occurs here. So let's analyze this deeply, the cross-sectional area of the combustion chamber and of the nozzle. This is a very interesting equation, which was specifically derived for describing rocket engines. So in the bibliography at the end, I added a page of NASA where they derive this equation. I would not introduce here today. So trust me, this is true. And the system of combustion chamber and the nozzle can be divided into 4 parts. Of course, the first one is the combustion chamber itself here, with the arrows indicated which exert pressure on the walls, everywhere on the walls of this combustion chamber. They are presented as vectors, of course, and we know if we added vectors, like, for example, this vector and this vector, up and down, they are cancelled out. So there's no net force at all, and the only region where this force is generated is here, because there's no arrows which would cancel those arrows out. So those molecules which push up, they generate this lift necessary to for rocket to move up. And how does it occur? Because basically the thrust force is dependent on velocity of the exhaust gas and of the mass airflow of this exhaust gas. So if the velocity is very high, then thrust, so the force which acting up, is very large, and this is we want for rockets to have. And this equation basically explain how this velocity is accelerated, because of course in the reaction chamber here separate molecules have very high velocities, but the net velocity of it, if we sum it up, it's very low. So we have to redirect this flow the one direction to actually contribute for it to contribute for the general thrust, so for the force acting up. And it's achieved through by this nozzle. At the convergent section of this nozzle, we have this perimeter m is less than 1. So if it's less than 1, this m squared minus 1 is less than 0, so it's minus. And dA is a cross-sectional area, and V is velocity. Didn't explain, but it's obvious, I guess. So here you see this cross-sectional area decreases. Yep. So dA is the change in the cross-sectional area is also on the minus. M squared minus 1 it has a minus sign. So if we want it to be mathematically true, this dV, so the change in velocity, have to be positive. So it accelerates. In the region here, where is the throat, we would not explain what is was going on here. It's just a point where those two sections, convergent and divergent nozzle section, they meet each other with m equal to 1. So it's, from a mathematical point of view, nothing happens here. But if we go at the right, there's divergent nozzle section where you have this m perimeter is greater than 1. So this m squared minus 1 is greater than 0. And dA, the change in cross-sectional area, is also greater than 0, because as we can see on this image, it increases. And if it increases, dA is The A is positive, this is positive, so the V, the velocity change, also has to be positive, so it additionally accelerates. And exhaust gas coming through those two sections actually is accelerated in this section, convergence section, and in the divergence section. And here is represented with this arrow, UC. U is the velocity here. UT is the velocity, is this vector, the throat. And here is the velocity of exhaust gas. So we see here that this arrow is much bigger than this, so the velocity is higher. And this is what we wanted to achieve here. Of course, I separated those aircraft engines and rocket engines, but there were some airplanes which used rocket engines actually, and they also may power some types of high-speed aircraft. The first aircraft to break the speed of sound, this guy, was powered by a rocket engine. As the first hypersonic aircraft, X-15, which also was powered by a rocket engine. Of course, we know that rocket engines are very generate a lot of thrust, so the force pushing forward is enormous. So this is exactly why those aircraft were the first one to break some records historically. Okay, I've mentioned this thrust, but now I would introduce you from the mathematical point of view. What is it? Of course, thrust can be explained in terms of jet engines and rocket engines, but for jet engines is a bit complicated, and we don't need this to understand the following section of the webinar. So this equation has two components, as we can see, the sum of the two components. The first component is mass flow rate of propellant times exhaust velocity. This is basically the change in momentum when the combustion reaction occurs. Of course, as we said with jet engines, when momentum is changed, so when momentum is changed, force must be applied. So this force here is the partial thrust coming from the change in momentum. Propellant is the same word as fuel, but for rockets, because propellant is a wider term, is an oxidizer plus fuel. In the jet engines, fuel is just what is stored in the, if we recall, the fuel is stored in the wings here. So when we say the fuel in terms of, when we explain aircraft, the fuel is just those hydrocarbons that are burned inside the combustion chamber. In the rockets, propellant is the fuel and oxidizer. This is the first component, this change in momentum. The second component is comes from the change of pressure here, because, of course, during the combustion reaction, the pressure is a lot bigger than inside the combustion chamber and the nozzle, actually, because if we would look here, we see that this pressure PE is not the same as the pressure of the outside. And this pressure differences also contributes to the general thrust, because we know from the definition of pressure is the force acting on some area, yes, P over A. And if we write it in a different way, we would say that force is equal pressure times area. So this is basically the change in the forces acting on the ambient side and the exit, another exit side. And of course, when the rocket is beyond the atmosphere, in the vacuum, almost vacuum, the ambient pressure, so the pressure of the outside of the rocket, is very low. So this pressure difference is at the highest point in the vacuum. So the thrust is slight bigger, and the thrust, this quantity, is very useful to understand what is a specific impulse. The specific impulse is a quantity allowing you to compare some engines and how efficient they are. Generally, impulse without this word specific is just change in momentum, delta P, or in other words, is the force acting on an object during some time dt. This is this equations. T is the thrust, because we analyze the specific force, thrust, so this is T, letter not F as the general letter for force, times dt some time. So intuitively speaking, we could say this is how much force was applied to you or other object during some time. And specific impulse basically says that you have to divide this impulse, so the maximum push you gained from some object, per weight of propellant, m times g0. G0 is standard gravity, 9.81, sorry, meter per second squared. And this is a quantity telling you how efficient those engines are. Because if we burn some amount of propellant in the combustion chamber, and if we generate some thrust from this, you can compare how much thrust you generated from, for example, 1 kilogram of propellant. So if the generated thrust is huge, then specific impulse is also huge, and because the efficiency of this engine is very high. Of course, this dt can be right here, mdt as a fraction, m over dt, and if you do this, you obtain mass flow rate. This is m dot times g0. M here is, of course, the mass flow rate of the propellant, and m dot g0 is the rate of mass flow of propellant burned in the combustion chamber. Yeah, it sounds complicated. Okay, this is basically this is basics, and as I've said previously, rockets, of course, they have specific impulse thrust higher beyond the atmosphere because of the bigger pressure difference here. Yep. And so a specific impulse also would be bigger. On this image here, there is some comparison of different engines, jet engines and rocket engines. Jet engines, of course, have higher specific impulse, because for jet engines, this m dot is equal only to mass of fuel burned, not propellant. fuel, of course, the mass of fuel is not as much as the mass of propellant in rockets, so you divide per lower, smaller numbers, and this is getting you a bigger number. This is one of the reasons why jet engines have a specific impulse higher. So they basically are more efficient because they have access to the oxidizer from the atmosphere. Rockets don't have this access. And of course, this is I would explain why these turbofans are so efficient. The specific impulse measured in seconds, by the way, is a very strange unit for this, but they are seconds. Turbofan, as I've told you earlier, here, has this bigger fan. This is why they are called turbo fans, because of this additional gigantic fan in the front of the whole engine. And this bypass air also generates lift, but the trick is that this bypass air is included to this thrust. But of course, this bypass air isn't burned, so it's those engines have this trick that this bypass air contributes to the thrust, but not contributes to the fuel burned. So the specific impulse is very big here. Of course, rocket engines don't have this big specific impulses. They are in the bottom line here because those engines are highly inefficient. They are highly inefficient because if we want a very big thrust, big enough for liftoff of the rocket, you need to accelerate exhaust gas to the tremendous speeds. And if you accelerate gas to speeds, I don't know, 10 kilometers per second, maybe, then you have to convert this energy from the chemical bonds of hydrocarbons, carbon and hydrogen. You have to convert this energy to kinetic energy because the kinetic energy is mv squared, scales as the power of 2 of velocity. So if you want to get very huge velocity, you have to convert a lot of energy of chemical bonds to the energy needed here. And because of that, this is the main reason why velocities are very high for rocket engines. And this is the reason why those rocket engines are at the bottom line here. And of course, propellant is counted as a fuel and oxidizer, not only fuel as with jet engines. Some methods to increase specific impulse we can see with kinetic model of gases. Basically, the most important are two things from this kinetic model of gases. The first one is very obvious, but it's worth highlighting that the higher the temperature, the higher temperature is, the higher also, of course, the thrust obtained. And this scales as exactly square root of temperature. And the most important one is mass of the gas accelerated, because thermodynamically it was of course proven later, that if the gas has very low mass, molecular mass, this is the mass you can read from the periodic table. For example, for helium is 4 grams per mole, for hydrogen as a molecule H2 is 2 grams per mole, and so on. If the molecule is very light, has a very small mass, then their velocity, its velocity is huge. For example, in this graph on the right, you have noble gases here, velocity and fractional molecules. For xenon, this atom have mass 200 grams per mole. I don't remember exactly, but it's very huge. And the average velocity of molecules, you see, it's very low exactly. Krypton is much lighter gas than the xenon, and thus this peak has slightly moved to the right side. And argon is lighter, and this peak also moved to the right, and neon and helium. And the helium, of course, is the second lightest element in the universe, and you see that for helium, the first thing you can observe that this range of molecules with high velocity is very big, because here you have for xenon, krypton, argon, very sharp peaks. For helium, you just have this smooth distribution. This is the first very cool thing here, and the second is helium. The average velocity of helium molecules is also a lot bigger than even neon, and they differ in mass in 16 grams per mole, and those 16 grams per mole exceeds this high difference. So you can raise this specific impulse here, so the efficiency of the engine, by raising chamber temperature. So if you have this chamber temperature, the velocity is higher, and then the thrust, and molecular weight. You can not increase but decrease, as those two graphs show us. We would move to the next section. The next section are rocket fuels. Rocket fuels, there are two groups of rocket fuels. The first is solid rockets, solid propellants, and the second is liquid propellants. Solid propellants, as the name states, propellant, so a fuel plus oxidizer, they create a solid mixture here. And liquid propellants, they are stored in the separate tanks here and here, so liquid fuel and liquid oxidizer on this image, and they are pumped up to the combustion chamber when the reaction occurs. In the solid propellant, the reaction occurs slowly at the beginning in the area where its mixture is ignited, and it expands higher, and higher. So this is a very fundamental difference between those propellants. How do they work? In the case of solid propellants, at the beginning, of course, as we know, nitro derivatives of organic compounds were used as those compounds which released a lot of heat during the combustion, for example. And here you have an image of nitroglycerin. Nitroglycerin is one of the so-called energetic materials. Energetic materials have in their structure both a fuel and oxidizer. So basically, if you have only nitroglycerin, this is enough, because NO2 groups, nitro derivatives of hydrocarbons, during the combustion reaction, when it's ignited, releases oxygen, and this oxygen is an oxidizer, and this oxidizer reacts with other nitroglycerin molecules, creating more and more heat. So basically, this is a cool thing here. But of course, those mixtures are even if they are used now, maybe in some small ballistic rockets or something like that, where it's not very important to achieve high speed or high specific impulse. Nowadays, different mixtures are used, and the most important one is called APCP. APCP is presented, of course, here with the cross-sectional area. So what do they circles mean? APCP includes in itself oxidizer. This oxidizer is ammonium perchlorate and NH4CsClO4 molecules. And those are the oxidizer, because of the chlorine has very high oxidation number, and this is why it causes very spectacular reactions. And as you use active metal, usually it's aluminium because it has high energy density. It's a cheap solution for this, and is responsible for approximately 10 to 15% of the overall thrust from the rocket. So basically, from the cheap aluminium, you significantly can increase your thrust of the rocket engines. And to bind those two components, oxidizer and active metal, here is shown those orange molecules are circles. Are aluminium metal atoms, and this is oxidizer ammonium perchlorate, those bigger regions. And the gray section here is the binder. The binder is needed to bind those things together, and because of that is also called solid propellant, because oxidizer with APCP and active metal, they need to be somehow combined to react well to produce thrust. And the other group is liquid propellants. Liquid propellants are the most used nowadays also, and we can divide them into three main groups, as I've described on the slide: petroleum-based, hypergolic, and cryogenic. What does it mean? For example, cryogenic pairs, most notably, of course, is liquid hydrogen and liquid oxygen. They are mixed together in the combustion chamber. And during the combustion reaction, H2O, of course, creates water vapor, exactly. And those cryogenic liquid propellants are the most efficient propellants we use nowadays, with specific impulse going up to 450 seconds. This is a very high number for a rocket, not for a jet engine, but for a rocket exactly. And you see this cryogenic and hypergolic. Hypergolic used in bipropellant rockets. The bipropellant rockets, they are rockets that it's enough to combine two propellants. Even without an igniter, they start burning reaction. And this is a very cool option for example, maneuvering to maneuver in the space, because you can in an easy way to move slightly right or left of this. The most used hypergolic propellants is monomethyl hydrazine, MMH, with nitrogen tetroxide N2O4. And kerosene-based fuel basically is a RP1 and LOX. LOX is liquid oxygen, and RP1 is a name for those petroleum part of this propellant. Basically, it's kerosene. It yields a specific impulses around 350, 320 seconds. So it's just okay, acceptable. And basically, from liquid propellants, I gave you 4 rockets with characteristics to compare them, and compare them with in terms of propellant used and specific impulse and thrust they got. For example, Space Shuttle, very famous rocket, creates thrust. Here is written 13 meganewtons, and their specific its specific impulse is 242 seconds. And this here, this shuttle used solid propellant APCP, which we discuss here. This is Space Shuttle. If we would analyze Saturn V, here we have, of course, liquid propellants, petroleum-based and cryogenic-based. And you can see that for cryogenic pairs, the specific impulse is higher than for this LOX RP1, so this petroleum-based one. And the difference is for rocket engines is big, yeah, 400 and 260. Proton K is a Russian rocket, and it uses those bipropellant mixture N2O4 and UDMH. Basically, they just mixtured together and ignited spontaneously. And here you have the characteristic of specific impulse. It's relatively high for the rocket engines. And here, of course, the same mixture and the same mixture. And it doesn't work like this, that the rocket uses only one type of fuel, because if we would analyze, for example, the modern Ariane 5 rocket, it's a bit more complex here. You would find boosters, booster first stage and second stage. And modern rockets have some characteristics with boosters and first stage and second stage, because they are more complicated than, for example, than, for example, Space Shuttle. Space Shuttle only has boosters and first stage. That's all. Modern Ariane 5 is much more complex. And here, for example, for boosters, you use a solid mixture. Ammonium perchlorate, aluminium, and HDPB. This is a binder which binds those together. And at the first stage, here is used cryogenic mixture of hydrogen and oxygen. And in the second stage, there is used bipropellant mixture of MMH and N2O4. And we can compare, for example, cryogenic pair with solid mixture, and we would see that for solid mixtures, thrust is 6.6 meganewtons, but for cryogenic, the thrust is approximately 1 meganewton. So solid propellants tend to generate a lot of more thrust, but the specific impulses, for example, he's not included the specific impulses, but we can analyze it here for cryogenic pairs where you have 440 seconds. It's a very big specific impulse actually. And if we would compare to the other solid propellant, for example, here the Space Shuttle, it was only 240 seconds. So this is the final stage of the rocket engines, of the rocket classical engines, where the combustion occurs, combustion reaction. And now we would go to the nuclear propulsion systems. But for now, I would try to explain to you how nuclear reactors work on Earth, because basically nuclear propulsion systems, nuclear reactors in the rocket that are built even now by, for example, NASA at this moment, the reactor core is very similar to the reactor cores we have on Earth. So at the core of the reactor, the fuel is typically uranium. Of course, we know uranium powder here. This is the image which illustrates the stages of processes, how we get nuclear reactor. I will explain now. And this uranium powder formed into small ceramic pellets here of uranium dioxide UO2. Of course, uranium is the most common element that is used in those applications. And these pellets here, cylindrically shaped, are stacked inside a long sealed metal tubes made of zirconium alloy. Here, these long tubes are called fuel rods. Inside of those fuel rods, there are a lot of these small uranium dioxide pellets, and those rods are grouped by the hundreds into a fuel assembly. The fuel assembly is some kind of a tube, a bigger tube consisting of a smaller tube. Smaller tubes are called fuel rods, as I told it. And in a cross-sectional area, you would say that for example, this gray tube is this fuel rod, and there are a lot of those rods, so they are grouped together into one assembly. And a large reactor core holds a couple of hundred such assemblies arranged in a lattice. And in a total, a reactor core contains 10,000 of fuel rods and millions of fuel pellets generating heat, and this whole system is immersed in water. The nuclear reactor looks like this, a top-down view. The photo was taken during the refueling process. Basically, of course, this pure uranium dioxide is not eternal, and you have to refuel it sometimes. And so, how do you do that? Basically, you just move up the assemblies where you have to exchange those pellets here. And basically after that, they are moved down to the reactor and it again works. So this is how structurally they are built, and the most important section of this is the chain reaction. Chain reaction is represented here. It relies on the uranium-235, as we all know. This uranium-235 absorbs through 3 neutrons. It's split into 2 atoms, smaller atoms, and it generates, of course, heat and some free neutrons, which in turn are absorbed by next uranium atoms, and so on. But in the nuclear reactors, there's one problem. You have to control this chain reaction. You can, because if you don't control oh no, what is going to happen? And how do you do this? You do this with using a so-called moderator. Moderator is for example, water is a molecule which can slow down those neutrons, because these neutrons which are created during this reaction are very fast, and you need to slow down. If you slow down those neutrons, they are much likely to be captured by next uranium-235. So the efficiency of this reaction, of this chain reaction, is higher. And this is how the heat is generated here. Of course, with providing heat, we know that heat comes from the chain reaction, and chain reaction occurs in the reactor core, and reactor core is built like this. And the moderator managing the neutrons and control rods. Control rods illustrated here, those are orange tubes. Control rods are for controlling the reaction, as the name states. If you can insert those control rods deep down and withdrawn from the reactor core, controlling the reaction. If you insert it deep down, control rods are made of Newton-absorbing metals such as cadmium or hafnium, and they absorb more neutrons if they are inserted inside. And if you withdraw those control rods, much less neutrons, much fewer neutrons is absorbed, so the rate of this reaction increases. So this is the way how you basically control it, the whole reaction. 2 most common nuclear reactors used on Earth: a pressurized water reactor and a boiling water reactor. So you have a generator of heat, a source of heat, and a so-called coolant. Coolant is the liquid which transfers the heat to the turbine through the circuits, for example, if they are, because if in a pressurized water reactor, the energy generated here is transported, water molecules catch them, and it's transported here. From the circuit, because it's basically in the one circuit is all it's happening, and it goes to the heat exchanger when where this heat is exchanged with the second circuit of water, and in this second circuit, this water is vaporized into steam, and the steam drives the turbine, and turbine generates electricity. While in a water reactor, the steam and water exist in the same circuit basically, and in a pressurized water reactor, they exist in two separate circuits. So you wanna need the reactor core, coolant, moderator, and of course control rods. How we can use this in space, this information? Basically, while nuclear reactors on Earth produce heat, so to generate electricity, nuclear technology can also be applied to spacecraft propulsion. The idea is to harness this tremendous energy of nuclear reactions to propel a spacecraft more efficiently than conventional chemical rockets. Conventional, I mean those on those relying on chemical combustion. And two leading concepts have been explored for nuclear propulsion in space: nuclear electric propulsion and nuclear thermal propulsion. These technologies promise higher performance for deep space missions, and both the European Space Agency and NASA is interested in those technologies and highly engaged right now. NASA is engaged in nuclear thermal propulsion engines, and ESA mainly in nuclear electric propulsion engines. So how do they work? We know how the heat is generated, so basically the idea is how do we convert this heat generated inside to a propulsion has a two-step approach. A nuclear reactor is used not to directly hit a propellant, but rather to produce electricity. And that electric power that is produced then drives electric propulsion thrusters through, for example, I know it can be ion engines like this one here. Yep. And this electric energy we receive from the converting the heat from the nuclear core is then fed into electric propulsion devices which expel a propellant at very high speed to produce thrust. It's expelled, of course, here through the nozzle. There are some there's an electron gun where you have those neutral atoms. In most cases, it's noble gas, for example, xenon or krypton, which is ionized. So you have here plus ions, and those ions are accelerated due to the potential difference, and this potential difference causes it to generate some thrust. Okay. The most common electric thrusters are ionized gas, as I said. For example, an ion engine uses electrodes or electromagnetic fields to push ions to exhaust velocities to 20 kilometers per second, far higher than any chemical rocket's exhaust speed. The specific impulse of electric thrusters is measured in the thousandths of seconds, typically even 3,000 or 5,000, so it's a huge amount, basically. The trade-off is thrust. is thrust. Electric propulsion provides very low thrust, often measured in millinewtons or newtons, comparable to the force of holding a piece of paper. So it just have a 1 or 2 newtons compared to meganewtons in classical rockets. They sip propellants very slowly, but by accelerating it to extremely high speeds, they gradually build up a large velocity change over time by thrusting continuously for months or years. In essence, nuclear electric propulsion spacecraft apply a gentle push on their spacecraft, but can keep that push going for a long duration since the nuclear reactor supplies a steady flow of power. And those were old examples. Project Prometheus, which was cancelled because of budget problems, and USSR's Topaz 2. Those projects existed, and now we wanna use them back. Okay. A new ESA's example. A recent European industry study found that a nuclear-powered electric spacecraft could cut 60% of transit time to Mars. Some battery problems. Sorry for this. I will be brief. A spacecraft could cut 60% of the transit time to Mars compared to a traditional chemical mission. The continuous acceleration or deceleration would mean a few months travel instead of half a year or more, the case in the case of chemical rockets. And the same study emphasized that with its high energy density, NEP offers disruptive advantages in terms of speed, autonomy, and flexibility, enabling longer duration missions and greater mission capability than either chemical or solar electric propulsion alone. And the last one is nuclear thermal propulsion. It uses a small nuclear fission reactor as the heat source for a rocket engine instead of a chemical combustion reaction. These are presented on the right side of the slide. In this propulsion system, a compact reactor core in the red color here that operates at a very high power density and temperature. The propellant, usually liquid hydrogen, is pumped through channels in or around the reactor core where it absorbs heat from the fission reaction. The hydrogen gas expands to very high temperature, Draco program. NASA, in partnership with the US Department of Energy, has recently accelerated NTP development, NTP nuclear thermal propulsion. In 2023, NASA and DARPA announced that the Draco program to test this propulsion engine in space by 2027. Under Draco, a nuclear thermal stage using a solid core fission reactor with enrichment up to 20%, enrichment of U-235, and will be built and flown in Earth orbit as a technology demonstration. The reactor will remain turned off, of course, until the spacecraft is safely outside Earth's atmosphere, after which it will be activated to heat hydrogen propellant to produce thrust. The demonstration aims to validate the performance and operations of this propulsion engine in space. This will be the first nuclear rocket test since the last Nerva ground test over 50 years ago. In addition to faster transit and nuclear thermal propulsion, upper stage could carry heavier payloads or more supplies for deep space missions than chemical stages due to its higher efficiency. And to sum up this table, which compares nuclear electric propulsion, nuclear thermal propulsion, and the chemical rockets in terms of thrust level, typical specific impulse, and advantages and disadvantages. Of course, for NTP, the specific impulse is the highest. For NEP is between the chemical rockets and NTP, up to 100 seconds. For chemical rockets is the lowest one, and for liquid propellants is the highest one within chemical rockets. So yeah, and I would end this webinar for in this point. And here is bibliography I used to present this webinar. 39 positions. And thank you so much.
Okay, so thank you very much. It was a really nice presentation. Yeah, so I think that we can finish it just as it is here. Thank you once again.
Okay, bye-bye.